Is this really that bad? So we're trying to get a 0 right here, of course. Okay. So if I take negative 75 times 1/2, well, that's negative 75 over 2. And I'm going to add that to 20 over 2. And it's going to give me negative 55 over 2. Okay? Just trust me on the arithmetic. Okay, if I make a mistake here, this is not the end of the world. Negative 75 times 1/4, that's negative 75 over 4. I have to add 4 over 4 to that. Is that negative 71 over 4? It's really that bad? Okay. And then I take negative 75 times 1/8 and add it to nothing. That should be negative 75 over 8. And then I have a 0 here. Okay? Oh boy. Okay.
If you go back.
What's that?
No, nothing.
So I'm not quite done. I'm going to do one more step here. I don't want to spend too much time on this. In all seriousness, this is not what I want to focus on. But let me multiply the second row through by negative 2 over 55. So negative 2 over 55. When I do that, the 2 is going to cancel with the 4. So I'm going to get negative 71 over 55 times 2, which is 110, I believe. 2 over 55, am I right about that? Yeah. Oh, and that should be positive, thank you. Okay, so that's a positive 71 over 10. And then if I also multiply negative 2 over 55 here, I'm going to get 75 over 220.
Yeah.
All right, great. That wasn't so terrible. Okay, not so bad. So I've got I always like to circle the pivots. I use the little diamonds around those. And each column corresponds to my variables in my linear system. So I have 2 free variables here, which are the C and the D. So I can then, if I take the second equation, I can actually solve for B in terms of C and D by subtracting to the other side. So the B is going to equal negative 71 over 110 times C, and then minus 75 over 220. We could reduce that a little bit, but I'm not going to. I'm just going to leave it unsimplified. So minus 75 over 20. Okay? So that is what B is equal to. And now I have to figure out what A is. Oh boy. Let's figure out what A is. It's going to be annoying. It's okay. I don't have that many. This will be the hardest thing I do today, probably. Let's see. So A is equal to negative 1/2 B minus 1/4 C minus 1/8 of D, right? From the first equation. And now I just have to put in what the B was. So it's negative 1/2 of the quantity negative 71 over 110 C minus 75 over 220 times D. Okay, and then minus 1/4 C minus 1/8 D. Okay, again, the idea of this is what I care about, right? You shouldn't expect numbers this bad, but the idea of what we're doing, I do want you to be able to do. So, what is this going to give me? 71 over 220 minus 1/4 is what the C scalar is, right? And then for the D scalar, I have 75 over 440 minus 1/8 of D. This is what A is equal to. Okay? Is everybody following so far? I don't know what this number right here is, but I'm going to give it a new notation. It's going to be a star. And this number right here is going to be a pound symbol. Okay? Because I'm getting too lazy to write it all out. Okay? So my P of x, now I can go back and write out what my P of x is. It's ax cubed, right? So what is that going to be? That's going to be star C plus pound B x cubed, right? Plus bx squared. Where's b? B is over here. So negative 71 over 110 times C minus 75 over 220 times d. That's all times x squared. And then plus cx and plus d. All right. Whew. So, to get my basis, I'm ready to get my basis. What do I have to do? Bust out the variables. Exactly. How many variables are there to bust out? Okay, the star and the pound symbol are not variables. Those are some numbers I'm too lazy to simplify, right? How many variables do I actually have? Just two. They are C and D, right? They are C and D. So I'm gonna go straight to the basis. I'm gonna bust the C out. When I bust out the C, I'm going to get star x cubed minus 71 over 110 times x squared plus x. That's my first basis vector. Okay? And then when I bust out the D, I'm going to get pound x cubed minus 75 over 220 x squared plus 1. So this is a two-dimensional subspace, right? Is that okay? That's not bad. So we got our answer. These are definitely a spanning set for every p of x that we could ask for. And they also are not LD. They're not dependent on each other. What's the if I asked you why are these Li, could you just explain that to me in a quick sentence? Let's say we're trying to convince ourselves that it actually is a basis, right? Let's suppose I actually want to convince myself that these are Li. Yeah.
Because all the degrees in the second term are not in the first term, or the other way. No, the first term is second. So you don't have x to do.
Right, so this polynomial is not in the span of this one, and this one is not in the span of this one, because they involve different powers of x. Or you could just simply say that they are not scalar multiples of each other. When you have only two vectors, that's a great justification. You just have to say, oh, the two vectors, they're not scalar multiples of each other, and you're good to go. Okay? So it was a little bit messier than I wanted that problem to be, but hopefully the idea is hopefully you're okay with that idea. Is that okay? Does anybody have any questions on that one? Okay, I want to find some more questions here. Are you guys, well, okay, so I want to do some slightly different things. Okay, yeah, let's do this one. I'm going to do a slightly more theoretical problem again. After doing that one, I think I need a break from the calculations. So let's practice. When you take Math 250B, you don't get a lot of practice with proofs involving like some of these concepts like linear independence and so on. So I would like to practice that a little bit. Okay, so let's do that here. Okay, so here's number 5. Okay, so suppose that T from V to W is linear and 1-to-1. So let's take a 1-to-1 transformation. Okay? If the set V1, V2, up to Vn is linearly independent, so Li, prove that the set that I get by transforming those vectors, so T of V1, T of V2, up to T of Vn, prove that that set is also Li. Let's see if we can do that. Okay. So this is a nice chance to refresh our memory about proving linear independence. If I want to prove that a set of vectors is linearly independent, how do I start it off? Because getting it started off, that first sentence to kind of get the proof flowing, is often the stumbling block. So I want to get this first part very carefully presented. So how do we prove? So let me just remind you what linear independence means. It just means that if a set of vectors is linearly independent, it means that the only way that you can cancel them out in a linear combination somehow is by putting zeros in front of those vectors. In other words, the cheap way. Just by throwing zeros in front of all of the vectors, of course that's going to cancel the expression out. But linear independence is saying that that's the only way you can do it. Right? So that's what we're trying to prove, is that the only way that we can cancel these vectors out in a linear combination is by throwing zeros in front of them. We're assuming that that property is already true for these guys. Okay, so where do I start with this proof then? This is actually one of my favorite proofs. Jennifer?
Do you write, since that set is Ly, you have A1, B1 plus A2, B2 plus dot 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 plus A and Bn equals 0 when A1 equals A2 equals dot dot equals An equals 0.
Okay, that's the popular thing to do that isn't quite right. Okay, linear independence, what it tells us is that if we have a set of vectors, of these vectors, a linear combination of which cancels out to 0, if we somewhere along the line find that, then the scalars will all be 0. Right? But that's what we've got right here. But the thing is, we need to focus on the fact that this is an if-then definition. So where should I actually start my proof from? Louis?
Start on the right side, the T of V1.
You've got to come over here at the beginning, right? And you've got to suppose that these guys do cancel out, right? So the first line of this proof is really, really important, right? It's a good chance I'm going to ask you one of these on Tuesday, right? Because this is really, you don't get this in 250B, but it's a very, very important definition. Let's assume that we've got our vectors canceling out. So C1, actually, does the book use C's or A's for the scalar? Is it A? I mean, I know what I use in the 250B flip book, but oh, I think it is A's. Yeah, it is A's. So let's assume that A1 times T of V1 plus A2 times T of V2 plus dot 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 plus AN times T of Vn. Let's assume that that equals 0. Okay? Then we need to show that A1 equals A2 equals dot 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 equals AN equals 0. Okay? So Jennifer, we will get to this, right? But we want to start with a linear combination on this side. Okay, so this is the setup. Is everybody good with the setup? Because like I said, that's often the hardest part for these kinds of proofs. Assume that you've got this linear combination that equals 0. You're going to try to show that you had to cheat to make it work. You had to just throw zeros in front of those scalars, in front of those vectors. Okay, so this is my starting point. Does anybody have a suggestion what I can do with that? Okay, well, which do you want to use first? It's linear and it's one-to-one, so let's not try and do it all in one step. So what can we actually do with this? Also, actually, so you mentioned one-to-one. What does one-to-one mean again? Okay, it's one-to-one means that if T of V1 equals T of V2, then V1 equals V2. Or is there another way to phrase that? I'm looking for a really, really quick thing that doesn't take much room to write. If T is one-to-one, if and only if the null space, right? The null space of T, or the nullity, which is the dimension of that, right? N of T is the 0 vector. Right. The only zero vector. That's what we're assuming here. Okay. So this is actually basically just the definition. Okay. It's very easy to prove that from the definition that Robert just gave me. Okay. So which one do you want to use first? The linearity part or the one-to-one part? So what can we do with the linearity then? So linearity means that t respects addition and scalar multiplication, right? We have those equations for that. So let me just put a star on this. Okay, so from star, since t is linear, what does that allow me to do with this box equation? So this is just a linear combination, right? It involves addition and scalar multiplication.
We can have transformation of two vectors and then add them together.
Okay, and I can just do that not just for two vectors, but for the whole expression, right? In other words, I can actually put all the constants on the inside and then pull the t way out to the front. Okay. This is something that when you have a linear transformation, I almost don't even think about it. I just like, oh yeah, that's obviously what I have to do. Okay, so I am just going to put everything inside of the parentheses with the t out in front. So this is going to be a1 b1 plus a2 b2 plus dot 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 plus an bn. Okay? So that's what we have so far. So t is linear, I can put the t way out in the front. Okay, so now what do I have? I have that t is killing this vector. So what do we now know? Go ahead. Sorry, Robert. I didn't hear you.
Since it's one-to-one, that vector must be the zero.
Exactly. The only vector that t kills is the zero vector. That's what one-to-one means. The only n of t is the vectors that are, so you may need to review that, right? N of t is the vectors that are getting killed by the transformation. So this is the set of v in v such that t of v is 0. Right. Okay, so since t is 1-to-1, right, then we know that a1 b1 plus a2 b2 plus dot 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 plus an bn, we now know that that is actually equal to 0. Okay, great. So we've got that. So, Jennifer, now I'm ready for you, right? I've got my linear combination of my original vectors. It's canceling out. But those vectors were Li to begin with. So I know that all of the scalars are 0. So since, I just like this proof because each step uses something from the assumptions. Since that original set is Li, then the A1, the A2, and so on. This is what we wanted to show. All of those scalars are just 0. They're all just 0. Okay, fantastic. So that's what we needed to show. Okay? So presumably this would not be true if t is not 1-to-1. And I am a big fan of, I've done this many times on exams in this kind of a class to ask for a counterexample for something. So I might have, this is like a nice part A, and then I would ask a follow-up, again, this is kind of a part B, or a follow-up, would be, give an example of a transformation from t from v to w for which the above conclusion fails when t is not 1-to-1. So if the transformation is not 1-to-1, then supposedly we can start with a linearly independent set, and after transforming it, end up with something that's not linearly independent anymore. Right? There are as many right answers to this as there are people in this room, right? We could all make our own example. But it is a little unusual. We don't spend a lot of time just making up transformations. It's not something we do all the time. We have to come up with a couple of vector spaces, and then we have to come up with a function. Let's not try to overthink it. Like, you don't actually need something very difficult. You just need to, you know, work your way step by step through an example. So for example, I mean, just to show you how casual this is, I say we can take any vector space V we wanted to. What's your favorite, what is your name again? Lorena, right? What is your favorite vector space? In other words, I'm just asking, give me any vector space.
Just like R, a real number?
Just the real numbers? Can we make it a little more? I mean, that would work, but that's only going to be one-dimensional, and it's like a really small vector space. Do you have another one that's maybe a little more than just R? Say again?
Like R3 work?
Okay, R3. All right, I'm fine with that. I just didn't want to use R because that looks like my scalar set. So let's use R3. Okay, and Michaela, what's your favorite vector space?
M 2 by 2.
M 2 by 2 of R. Okay, perfect. Great. So we take that one. And we're looking for a conclusion that fails when T is not 1 to... Oh, you know what? I'm going to change your favorite space. Actually, I'll change your favorite space. You know what I'm going to do? I'm going to change this right away to R5 because I know that no transformation from a bigger vector space to a smaller one can be 1 to 1. I'm looking for T not 1 to 1, and if V is bigger than W, I'm now reminding you of something else, right? We talked about this. If V is bigger than W, you've got to have collapsing arrows, right? So if I just do this, I won't even have to check if T is 1 to 1 or not. I'm going to know that it's not 1 to 1. Okay, so then I need a function via, so then let's define T from V to W via T of, well, it's going to be A, B, C, D, E, right? I have 5 inputs, and I need to come up with a 2 by 2 matrix for an output. And I'm wondering if anybody has an idea what we could do here. We already know that whatever we do, it won't be 1 to 1. This is your chance to create a function. You do have to be careful. You have to make sure it's linear. So don't put something like an A squared in the matrix or anything like that. That won't be good. But and make sure that, so you're going to have to make sure that the 0 vector goes to the 0 vector. And all those things have to be true about it.
How would you put like
A, B, C, and D. We can do that. Just so you know what I would have done, I would have just made my function that. Because now, the set over here on the right side is going to literally be a string of zeros, which is about as LD as it gets, right? And then you would just have to make up some linearly independent subset of the left side. But let's take, this is okay.
No,
No longer.
No, this is good. This is good. I just wanted to show you another, like the fastest possible way, right? So we can just do that. So what I would hope to do now is I need to find a linearly independent set over here. Now the n doesn't have to be a big number. I could just choose n to be probably 2. I just need to take 2 vectors that are linearly independent over here, that their output, once I plug them into the transformation, the result is not linearly independent. So that I just want to illustrate that this is, so I need to come up with my set. So the set V1, I'm just going to use two vectors. Let's not make it unnecessarily complicated. So I'm going to take a 5 tuple and then another 5 tuple. Whoops. 5 tuple and then another 5 tuple. Okay. Somebody want to give me some specific numbers?
Wait, why did you put just 2? I thought we were in R5.
The n is not related to the v and the w here. This n is not necessarily, the dimension of v is 5, the dimension of w is 4, but this n is some other number that's not part of the dimensions of v and w. We don't actually have to make that connection.
Why that?
Well, just because this thing we just proved doesn't depend on the dimension. Do we ever see the dimension of v or w